All right. Everyone. So we'll be reading together. This is a summary of our test and but so I believe if we follow together. So first of all, I want to talk about what is it meant. So the meaning of everybody knows what's the meaning of SQC, which is statistical quality control. So together, statistical quality control them of performing inspection ensure that the quality of the product produced is as per. Now, what are those statistical tools that are generally used for the purpose of exercise enhancement of productivity, creation of customer confidence? Those are, we have some out of our notes. We have the 7 statistical tools. They generally know histogram, chart, flow chart, scatter diagram. So the ones we have, the defect chart, the chart, then the number of defective charts. Read through the handouts, you'll see them. Now, because of this video, I will control chart. Control chart, this is a graph which is over time, comparing which leads to what? The conclusion about whether the process is in control or is unpredicted by some special causes of variation. At the number 2, our assignment. So, so the control chart for X bar on certain dimension of millimeter. The subgroup sizes are computed for each subgroup. Summation X bar is equal to 4 and summation R is the value of the process is. We're supposed to know X bar. Formula for X bar of the subgroup, which is the big N. So then highlighted here where N is the number of subgroups. Construct, they say compute an R chart and estimate the value of processes in statistical control. When you want to compute for, you have to first the 3 sigma formula for R is R bar plus or minus what? x bar. This for x is this is the upper D3 R together. To make up this, we have x bar bar, which so x bar bar over n. So we're 2.83. Our capital N is 20. So when we do, so this x bar in this formula, which is for the summation of, and they give us summation of R, which is, then our N still remain 20. It gives us 3.169. So that is, so we have sigma standard. Sigma for this one is different. This is standard. The formula for standard deviation over D2. Where is D2? Well, D2 now on our, when we impute it, divided by 2.059, our standard deviation. The root of n times it by 3, and small n they're talking about now is the subgroup, which is, so when you 3, so this is it. We've gotten so for this D4 in the table, so value for nothing but this from the table. Now let's compute chart, the 3 sigma for now. What we have only plus here is got, it is one carrying minus in between those values. So our look at it here. Our 3 sigma x by 3, we put it here. That now for is going to be equal to which is equal to this, remains 20. Sorry, there's a wrong calculation here. They mean 6415 minus 123. When you solve, you have 20.5185. So we are done. Now for R chart is now if you check our D4 in the table, we have it to be what? 2.28. So since it's 2.28, 28 times here is 0.169. Then you get your answer. 3853. It's a waste of time, though I don't really know what is happening. So you don't have to think about them too. Boundary as a lower class boundary from the lower control limit, R bar, which is equals to there's a written down rule that says from a subgroup small n to be less than 6 below to 0 is always what? 0. Take note. Subgroup is less than your D3 is always what? 0. 5 is still 0. So that's why we have D3 here to be what? 0. Multiplied by R bar, which is our 0. So we are done with that. Before you try attempting them, use in turning a shaft 0.75 plus or minus 0.1 millimeter towards taking each of these shafts are given below. Saying is that pieces, this is them, this is the 45, and they try them out the process. Now, first thing I want you to understand, they ask us to compute the 3 sigma and R. We should construct the two formulas. When you talk about 3 sigma for R, you state that what? But if the question says state that you should construct, so we should construct the X. Now the X bar and the R chart and this that when the mu, you are not giving mu and sigma, A to D2. I hope I'm cleared. And sigma are given. I will get to that. A new sheet. We know that 2, 3, 4, 5, 6. So we are going to sum up this one. 20, if you can see here, we're going to sum up this 23.77 plus 23.80 plus 23.78 plus 23.73 plus 23.76 plus 23.75 divided by 6 is equal to this, 23.75. So that is the result. So similarly, for each of the calculation we're going to do for each group. So that means if we do for this first one, when we solve for this first one, we have for day 1 is going to be equal to 23.765. Now the next one, you plus this plus this plus this plus this plus this plus this divided by 6. When you do it, it's going to give you 23.77. Now the next one, where you add this plus this plus this plus this and divide it by 6, is going to give you 23.7716. You do it for all of them and you get their values. Now when you get their values, that is when you now use the formula x bar over n. So now x bar is equals to summation of x bar over n. Now x bar here are for how many groups? 8 days, which is 8 groups. So that means you are going to add up all those x bars and divide it by the number of the s bars that came. So since we are having 8 different means, that means we are going to have x bar to be equal to 23.765 plus 23.77 plus 23.7716 plus down to the last one you got, which is 23.7667. So you now divide it by 8. So when you do that, you have what? You have your answer for this particular S bar. So when you do that, you're going to have this. We're going to have 696. As you can see it here, that's what they did. So after getting this one, it means you have gotten x bar. So since you have gotten x bar, the next one now is getting r bar. And we know that r bar is what? Summation of what? R over capital N, which is equals to. So how do you get r? How do you get r from the question? It's very simple. You say the highest minus the lowest. So in this case, if you check, the highest here is 23.80, then the lowest in that same group is 23.73. So when they are minus, if you minus it, you have 0.07. So this is it. When you do that for this group, you have 0.07. You do that for this group, you have 0.11. Let's check and see. The highest is 81 and the lowest is 70. So when you minus, you have 0.11. The same goes for this. So that's how you keep doing them. Then you get all the r's for the 8 groups. Then now you add all of them together and divide it by the number that appeared, which is 8 times. So you do that, you get your answer to be 0.0675. Do we understand? All right. So the next now is, since the mu and the sigma were not mentioned, we use for X bar chart, which is this. So we use this formula, plus A to R bar. So for upper control limit of X bar is equals to X bar plus A to R bar. So we know that when we solve for X bar, we got our formula to be, our answer to be what? 23.7696. See it here. Then the plus. Now our A2 can be getting from the table. If you can't get it from the table, we can actually as well get it from the formula. This formula that says A2, where A2 is equals to 3 all over the root of n, then D2. So you just get your D2 when the subgroup is 6, then you multiply it by your R. So, but you can get A2 from the subgroup. So when you get A2, you multiply the A2 value and multiply by 0.0675. So this is going to be equal to 3.802 for the upper limit. Then for the lower, the difference between this and this is just the minus sign. Then you get for the lower control limit. So now for D3, it's still the same thing. Sorry, for R, it's still the same formula with the first one. D4 R bar, D3 R bar. Like we said, you can see they say for subgroup of 6 or less. So once your subgroup is from 6 down to below, then you know that your value is what, 0. The subgroup they are talking about is not this general group. It's not from here to, it's not this one to this one. The subgroup that is from each group here, we have how many? 6. So that is it. I hope you understood. So that's that. So now, process capability. The next one is, they say we should find the process capability, which is what? 6 standard deviation, which is equal to 6 sigma, which is equal to 6 R bar all over D2. So we know how to find that now. So this is going to be 6 times our R bar that we solved. We got 0.0675 divided by 2.534. So this is the value you get in a subgroup of 6. Remember the first one for a subgroup of 4 that we did. Now this one is for the subgroup of 6. So don't say the D2 are the same or true. No. For that one we got 2.28. This one we got 2.534. So you should know it. Then the problem is solved. So let's look at the third problem. And the third problem says, the following table shows the average of the spindle diameter in millimeter for what? For 30 subgroup of 5 items each. So this is the subgroup. can see the question says the following table shows the average of the range of speedo in millimeter for 30 subgroup of 5 items each. So now when you look at this place, this is 10, 15, sorry, 10, 20, 30 for the R bar. Then this is 10, 20, 30 for the R. So what you're expected to do here now is, they say for the first 20 samples, so now we're taking a sample from the population of 20. So we know what 2 rows should be up to 20 samples. Set up on X bar chart and R chart. Plot the next 10 samples on the what? The chart to see if the process continues under control, both as to average and range, as also find the process capability. Now in this case, what do we do? Now in this case, you can see that the question said we should set up R bar chart and R chart. You set up X bar chart and R chart. Plot the 10 samples on this chart to see if the process continues under control, both as average, range, also find the process capability. So now when you take a summation of the 20 subgroup, that is this X and this X bar, you have this 909.170 divided by 20. So divide by 20, you get this. Then for the R bar, you're going to pick this and this, add them up, you get this. Divide by 20, you get this. Then our sigma is R bar all over D2, which is equal to 0.3125 over 2.326. It's equals to this. Then now we know we are going to find our sigma X bar. Now you know this standard deviation is sigma, so it's going to be sigma all over the root of n, which is this. And our n here is what? It's 5, because from the question it says the following table shows the average and range of a speed diameter in millimeter for 30 subgroup of 5 items each. So our small n is 5. So we know the only thing that's not given here is just the 3. So, but by the formula, we have X bar plus 3 sigma X bar. So what are we waiting for? You just compute. So when we compute, then for R, it's still going to be the same thing. They made a mistake. This is supposed to be D4. This is supposed to be D3. Now for D4, the value there is what? This for 5 samples. Remember the last one we finished up was for 6 samples, so we have 2.11 X bar, 2.11 times our R bar. We'll get our value. Then the next one is 0. Are we clear with that? So we are going back to our notes. I think we have successfully solved 3 problems. So in our notes, the next thing we're going to look at is benefit Benefits of statistical quality control. We know we said efficiency, reduction of scrap, is detection of faults, adherence to specification, increase output and reduce wasted machine and man hours. Efficiency utilization of materials resulting to higher productivity, better customer relationship through general improvement in product and higher shares of the market. Creating quality awareness in employees, elimination of bottleneck in the process of manufacturing. So we are back to control chart again. So what do we understand by control chart? We say it's a graphical representation of collected information. The information may pertain to measure quality characteristic of samples. Control chart are categorized into two. There's a difference between categorizing and type. Now, when we say types of control chart, we have attribute control chart and variable control chart. The category of control chart, we have the what? The chance pattern control chart or the common cause variation. So we have the chance pattern of variation as one of the category. Then the second category is the assignable cause pattern of variation. So what pattern of variation are we having? We have the chance pattern of variation or common cause variation. Then we have the assignable cause pattern of variation. Now we're going to look at them. That is, by the way, you try to check what is their difference. Okay, let me explain something. Chance pattern of variation. This is usually caused by human, is inherent. Why the assignable cause of variation it comes from it's more like an inherent something, like it comes from the product, it can come from the machine, it can come from the efficiency of the material. Why this chance pattern of variation is mostly caused by human lack of skills, negligence, ignorance, stuff like that. Then this chance pattern of variation, it can be controlled, but the assignable cause cannot be controlled because it's more like a default something. Then another this thing is that the chance pattern can be easily detected, while the attribute assignable cause is hardly detected because it just takes a few signs of different. Let's say, for instance, if you observe different pens, maybe even from their cover, you discover that if you carry 10, you will see small difference. Even the difference, you have to pay very close attention. No? And those are assignable cause. But when the chance pattern of variation, that one is very, very obvious. Just like, for instance, now, me that used to grind corn for you, tomorrow you come, my boy grind corn for you. You now discover, the way I grind my own is soft than the way the man grind it. So those are chance cause. But I don't know. You need to check. I don't know if I'm intertwining these two causes, but that's their difference. So we have warning limit on control charts. We have the 3 sigma, which is called the action limit, and we have the inner limit, which is said to be 2 sigma warning limit. Now, type of control chart, we have variable control chart, which consists of mean, which is the X bar, then the range, which is the R, then the standard deviation, which is the sigma. Now, the attribute control chart, this is the fraction defect chart, which is the P chart. We have the chart for defect, which is the C chart. Then we have the chart of number of defectives, which is the MP or D chart. So before we move further, we want to know what is specification. Now, we say specification is the maximum and the minimum limit of variation of individual item as mentioned in the product design. Specification is just like a allowable desire. It's more like what you desire. Okay, for instance, let's say for instance, you desire for somebody to make palms for you. So you said, if these palms, I want it as slim as possible, and I don't want it to pass size 45, either 40 small or 40 big, but it should not pass 45. Now that is your specification. So it is a maximum and a minimum allowable what design or desire of a product output from a consumer or a producer or a customer, anyhow you want to put it. Now tolerance limit now is within that space of 40 size 40 and 40 big or 40 small. The minimum error you allow is that you should not exceed 40. Let's say for instance, maybe you want it to be 40 to 40 and a half. So once it passed 40 and a half, you are not wear it, because you know that you don't want to wear tight shoe that will be causing you pause. So instead of making it a tight shoe, just give it a half space, small, so that even when it's too big, when you grow, your leg will fit in. Now that's tolerance limit. I just put it in a layman language, you understand. But in the definition, I say is the difference between the high limit and the low limit in which the margin allowed for variation. So what he's saying is that it is the difference between the upper limit and the control limit. Just like the way we have from the 3 sigma, what. The difference between them is what? The tolerance limit. So if you want to remember, you say the difference, it is what? Also the allowable limit a product is said to go far from accuracy or perfection without implication. So, when you have a shoe that is 40 and a half, it's still not far from your perfection. But when it's size 41 now, it's far from your perfection. Are we getting it? So that is just the whole scenario. So yeah, I just fished out the formulas when you're doing a control chart. When mu is given, when mu is given, when sigma is given, you use mu plus a sigma, and we know that a is always 3 all over the root of n. So when you see a1, what do you now put? What is now a1? Now it's a1 will be all over d1. I think so. So that be 3 all over the root of n d1. I guess that should be a1. But let's just stick to what we have. So they say when the mu and sigma are unknown, you use this formula. But when r is also unknown, you use x bar plus or minus a1 x bar. Okay. All right. Now let's go to the next page. Comparison between attribute chart and variable chart. Now we can use the example as one of the comparison. Example of variable chart are x bar, r, and sigma chart. Then for attribute chart, they are what? P, MP, C, and U chart. Now variable chart, another different comparison is that variables, or let's just say a variable chart measures value of characteristics. Variable chart measures values of characteristics, while the attribute charts measures or control of proportion of defectives or number of defectives per unit. Control the proportion of defectives or number of defectives per unit. Then the 3 says the variable charts provide maximum utilization of information available from a data. While AC chart, that is attribute chart, says what data required often already available from inspection record. So that means in another shell, the variable chart deals with what a primary source of information, while the attribute chart deals with secondary form of information. If you want to remember that aspect, say provide maximum utilization of information available from data. Then this one says what data required are often already available from inspection record. Another comparison is that they are not variable charts, they are not easily understood unless trained. So another thing is that we need someone with prior knowledge about variable chart before we can provide meaningful information. So that's why they said they are not easily understood unless training is provided. Then the attribute chart, they do not provide detailed information for control of individual characteristics. Well, you can also use this attribute and their comparison as their difference, in case you are asked in the question. Then the next one is we want to look at a simple problem that involves attribute chart. So are we together? So one of the problems is if you go to unit 2, the problem 1, you see there they said the following are inspection results of magnet for 19 observation. Calculate the average fraction defective and 3 sigma control limits. Construct the control chart and state whether the process is in statistical control. So many may like, I saw this question. Which formula should I use? Why will I do this? Should I do this? That? No. Now calm down and listen to the question. The following are the inspections results of a magnet for 19 observation. Calculate the average fraction defect. Average fraction defect is talking about what? P. Average fraction defect is talking about P. Is it P? Yes, it's talking about P. So, and what 3 sigma control limit, construct the chart and state whether the process is in statistical control. So the average size, normally, you first thing you have to calculate is the average size. Now the average size is always our n in this formula. It's always our small n. The average size is always our small n. Now the average chart is always getting from the, how am I going to put it? The main values. I have to go and look for this thing. Give me a minute. All right. This is it. So the first thing for us we need to calculate is, now this is what I'm talking about. Number of magnet inspection. Now from the question it says the following are the inspection result of a magnet for 19 observation. Calculate the average fraction defect and 3 sigma control limit. Construct it. So what we're talking about is the magnet, right? So here is number of magnet inspection, and here is number of defect magnet. So the first thing you're going to calculate is the average sample size. So the average sample size is going to be this divided by how many are there, which is 19. So when you divide this by 19, you get your n. This is equivalent to your what? Small n. Now, for defect, the formula is P equal to P bar plus or minus 3 into brackets, sorry, into the root of P bar Q all over N. But we all know that Q is what? But Q is equals to 1 minus P bar. In that case, having done that, we're going to have the average fraction defect. Now we have to find P bar, which is the average fraction defect. That is the mean of the fraction defect. So the mean of the fraction defect is going to be number of defective magnets divided by number of magnet inspection. Number of defective magnet divided by number of defective distance. So when you do that, you're going to have 0.0731. So when you divide it, you have 0.031. So you have gotten your P bar. Now looking at your formula, there is no unknown. You have P bar already. This is the plus or minus 3 is the number. Now we have another P bar, which is still the same as this. Now the Q is the same as 1 minus P, so you can substitute it to be open bracket 1 minus P. And 1 minus P bar is still the same as this. So when you put it divided by N, I always tell you that your N is this, the average sample size. So when you substitute, you get your answer easily. So that's what they did here, and you can see they arrive at this. So is it understood? So now that it is this, it doesn't stop there. For upper control limit now, we said is plus P bar plus 3 into the root of P bar open bracket 1 minus P bar all over N. So that is for upper, then the lower is going to be minus in between them. So when you do it, you get your answer. Then after doing that, okay, there's something I almost omitted. After doing that, you have to draw your conclusion. Now we conclude that the resulting control charge sample numbers second and fourth are going above the upper control limit on the sample number 19, which goes between the lower control limit. Therefore, the process do not exhibit statistical control. Some of us be wondering, how am I going to do this explanation? Now, what they are just simply saying is that when you look at your value for your lower control limit, you have 0.10. So your upper control limit, you have 0.108. And your lower control limit, you have 0.044. When you solve properly. Now, you go back to the table and check fraction defects. Now, that fraction defect that I'm giving you the question, anyone that goes above the upper control chart, which is 0.1018. Now, when you check, you see the number 2 is above, is giving us 0.109, and in our upper control chart we have 0.101. So you can see, so it's above. That means it's above the control limit. Let's say for instance, if we have something like this, this is upper control limit and lower control limit. Now here we have 0.1018, and here we have 0.0444. Now the first, if you check this value, 2 is already going higher than this place. That means it's not exhibiting. Then you check for 4. 4 is one higher, 0.114. So it's one higher than this. So you say what? In conclusion, we conclude that from the resulting control chart, sample number what? 2 and number 4 are going above the what? The upper control limit on the sample number 19, which goes below. Is it below? No. Which goes above the upper control limit on the sample number 19. Okay, that means the number 19 again goes below. If you check, yeah, sorry, gives us 0.004. So we're having 0.038. So it goes below. So number 19 too goes below. So that means they are scattered. So therefore, the process does not exhibit what? Statistical quantity control. I hope we all understood. It's easier. Then let's look at another problem. Are we together? Problem 2 says, under unit 2, say a certain product is given 100% inspection as it is manufactured. Let me invite some people. Yeah, we're back. So the second problem under unit 2 said a certain product is given 100% inspection as it is manufactured, and the resulting data are summarized by the hours in the following table. 156 hours of data are recorded. Calculate the control limits using 3 sigma control limit and indicate the value that are out of control. Okay, this one is simple. It says a certain product is given 100% inspection as it is manufactured, and the result data are summarized by hours. In the following table, 150 hours of the data are recorded. Calculate the control limit using 3 sigma control limit and indicate the value that they are out of control. So first thing, I think this is the question. Let's see. This is the question in case my handwriting is not clear enough. Now in this question it says a certain product is given 100% inspection as it is manufactured, and the resultant data are summarized by the hour. In the following table, 156 hours of data are recorded. Calculate the control limit using 3 sigma control limit and indicate the value that are out of control. So first thing for us, I said, if you